So the next thing I'd like to talk about are the design challenges associated with PCI Express 3.0. And when we sought to create the PCI Express 3.0 standard, our objective, which has been consistent for all of the releases of the standard so far, has been to double the throughput of devices that are based upon that standard. So for example, PCI Express 2.0 is twice as fast as what we had for Gen 1. PCI Express 3.0 is intended to be twice as fast as what we had for Gen 2. And even looking ahead, Gen 4, our goal is to be at least twice as fast as what we had for Gen 3. So for Gen 3, we ran into some issues, because to double the performance of a Gen 2 device, the easiest way to do that would have been to double the data rate. Gen 2, PCI Express 2.0 operates at 5 gigatransfers per second. Easiest thing to do would have been to double that to 8 gigatransfers per second. Well, the faster you go in gigatransfers per second can result in significant challenges when you try to propagate that signal through a printed circuit board. For PCI Express, we consider two different types of printed circuit board form factors. One we refer to kind of as the client channel, which is essentially about 10 inches in length, maybe 25 centimeters, and has one connector in it. Relatively a short channel. It tends to be more reflection dominated from a signal integrity standpoint. The other type of channel that we use in PCI Express that we consider part of that solution space is the server channel. The server channel is 20 inches in length, so it tends to be more loss dominated and consists of two connectors. So that's really probably the more challenging element of PCI Express 3.0 that we need to support at 8 gigatransfers per second, is that long loss dominated requirement for support of that particular channel form factor. Now, when you look at a signal that goes 8 gigatransfers per second at the end of a 20-inch channel, the eye heights can be tremendously small. In fact, without any type of equalization, either on the transmit side or the receive side, the eye is closed. So Gen 3 represents a closed eye specification in that form factor. So that represents a significant challenge from a development standpoint, because you have to essentially have the hardware in your receiver and as part of your transmitter that helps to mitigate some of the effects of that long channel. And that's what PCI Express 3.0 brings to the table, and it also is the source of a lot of the challenges that we face when we go to make measurements. So a couple of the common questions that I get since I work for a test and measurement company is, how much bandwidth do I need for, say, my oscilloscopes for doing transmit analysis? Well, keep in mind that bandwidth and how much bandwidth you need for any given standard is essentially driven by one of the same requirements, which is how fast are the edges that you tend to measure. Now, as we were developing the PCI Express 3.0 standard, we based our requirements on bandwidth on assumptions of what process nodes people were going to be at from a silicon standpoint. And we were generally observing edges, say at 80%, 20% thresholds of around 45 to 55 picoseconds, in that range. And certainly at the end of a channel of FR4, if you're making those car electromechanical measurements, we find that 12 gigahertz of bandwidth is sufficient for doing that. And within the PCI-SIG community, you'll see more in terms of what we've written into the test spec, as well as in the test procedures that will point to 12 gigahertz bandwidth being the essentially the target bandwidth that we want you to use. More bandwidth, certainly good. Higher sample rates can be good because they can help to lower noise if used appropriately. But to give you an idea, the overall rule of thumb is the equipment that you used for Gen 2 certainly adequate for doing measurements for Gen 3. And I think that's going to be good news for a lot of folks. But keep in mind, edge rates have a tendency to go up as the process node technologies shrink. So as the processes get smaller and smaller, like 28 nanometer or even below, we can start to see faster and faster edge rates. But another factor that contributes to the bandwidth requirements for Gen 3 is the fact that for the first time, we've specified that the receiver has to have a level of equalization. This equalization we refer to in the standards community as the reference equalizer. Now, we don't say from the PCI-SIG standpoint exactly what your reference equalizer needs to be. What we do say is whatever you do for a from an equalizer standpoint on the part of your receiver, has to be at least as good as what we refer to as the reference equalizer. So it can be better, but it has to be at least as good as the reference equalizer. So the next question obviously is, well, what's the reference equalizer? The reference equalizer consists of a CTLE followed by a single tap DFE. And the specifics of those requirements are written in the PCI Express standard, so I'll refer you to that. But those two in combination form the reference equalizer. And when applied to a PCI Express Gen 3 signal at the end of the channel, they'll open the eye up. At least assuming that there's proper transmit de-emphasis that's being applied as well. So that's the reference equalizer. Now, the reference equalizer for the CTLE definition also has, as part of that CTLE definition, a limitation on the input bandwidth of the receiver. And this also can contribute to our understanding of what bandwidth is necessary for doing Gen 3, because essentially the second pole of that CTLE equalizer limits the bandwidth of the equalizer to 8 gigahertz. So there's essentially an 8 gigahertz bandwidth on the input of the receiver. So that's something that isn't quite obvious as you read through the specification, but again, that helps to guide us and direct us. So the things that we see as being the biggest challenges for PCI Express are really starting to focus more on the receiver side than the transmitter. The transmit analysis is still as important as it ever was, but what we're finding as being more of our focus of work in terms of the body of work that we do, it's really all about the receiver now. Because it's in the receiver that we're able to open the eye up and are able to achieve the target bit error rates for the standard itself.